Okay. Hello, everyone. My name is Arshag. I'm a postdoc here in Virginia Tech. My advisor is Sophia Economou. I prepared a tutorial on graph states and how it applies to different quantum technologies with her help. And that's what I'd like to present to you today. Okay, so just to give you a brief overview, I first want to kind of motivate what graph states are. So talk a little bit about entanglement, and then we can define graph states. We can talk about how those graph states change when you make measurements. And then we can talk about the application of these types of quantum states. Okay, so let's start by talking a little bit about entanglement, just to have a general picture of what's going on. So I want to think about an example where our qubits are just a bunch of spins that are prepared in some state. And the physical observables that we have are basically the spin direction along the z-axis. So in other words, that's the Pauli z. We want to, our observables are the Pauli z operators. So quantum mechanics will tell us how to compute the average experimental value for these types of observables, right? It's just by taking the bracket of the Pauli operator with the state of our spin. And generally speaking, each measurement outcome is random. So this number will tell us what the average value is, not what the individual experimental outcome would be. Right. So with that said, let's think about two qubits. That's the easiest way to think about entanglement. So let's say you have two qubits and you prepare your qubits in two different ways. So one way of preparing your qubits is that you prepare them separately. So your qubit 1 is in state psi 1, as you see over here, just as superposition of being in spin up and spin down. And same for qubit 2, you prepare it in state phi, let's say, with some other superposition of up and down. That's one approach. So you prepare the qubits separately. The other approach is that you prepare them together or collectively in some sense. And that's kind of the most general way of preparing your qubits. So then you will have a superposition of all possible values of their spins, right? So this is the most general way of preparing them. And what we could measure for our qubits is the spin directions, right? So we can measure the Pauli z on each qubit. And if we find spin up, that's a +1 for our observable value for z, the Pauli z's. And if it's -1, then it's a spin down, basically. Right. So the quantity that we want to be interested in is this parity quantity. So parity is just a product of the two Paulis, so z1 times z2. And physically, what it tells us is whether the spins are parallel or anti-parallel. So if you measure this observable and you find the value +1, it means that the spins were parallel. So either both up or both down. And if you measure this observable and find the value -1, it means the spins were anti-parallel. So up, down, or down, like this. Right, okay. So with that said, let's think about our qubits. So assume the qubits are prepared completely independent, right? So you have the state psi for the first qubit and the state phi for the second qubit. And now you measure the spins. So if you measure them separately, you will find, let's say, values z1 and z2 for your observables. Here I'm measuring the experimental values that you find by little z, and big Z represents the Pauli. Right. So what would the parity of the qubit spins be? So to measure the parity, right, all you have to do is to just take the product of the values you found from the experiment. So for instance, if you found the value +1 for the first qubit and -1 for the second, then the parity will just be 1 times -1, which is -1, meaning that the spins are anti-parallel, which is the case, right? So that's how you would measure the parity if you were to prepare your qubits in this way, completely independently. And that's just a consequence of the fact that the total state of your qubits are just a product of the individual states, since you prepared each qubit in its own lab, basically. But if you think about measuring the parity of your two qubits, then there are cases where just measuring the individual spins is not sufficient to tell you anything about the parity. So I want to give you an example of when would that happen. So think about the following preparation of your two qubits. So you have two qubits that are prepared in equal superposition of both being up and both being down, right? So if you were to measure the spin of any of the two qubits, let's say the first qubit, on average, you will find the value 0, right? So there is no preferred directionality for the spin of the first qubit. And similarly, if you measure the second qubit spin, you'll find that it has an average of 0. So it's equal likely to be up or down. So it has no preference of being up or down, basically. But if you measure the parity, you will always find that it's +1, meaning that the spins are always parallel to each other, which is the case from here, that you see, from the state. So that's very unexpected if you had, basically each qubit was equal likely to be up or down. There is no reason why when we measure the parity will always be parallel. You should also be equal likely to find them to be parallel, so either both up or both down, and equal likely to find them to be anti-parallel, so one up, one down, or the other way around, right? But here parity is completely deterministic. There is no randomness in the parity. So this tells us that the state of our qubit should not be separable. So meaning that it cannot be written as the product of the two individual qubits. Because otherwise we would have found that there is no particular particular value that the parity would take. So on average, it will have a value 0. But that's not what we find here. So the statement that this state is separable in the sense that it can be written as the product of the two individual qubit states will not be true. Right, and that's what entanglement is the fact that you cannot separate the state into individual qubit states, or the product of the individual qubit states. So these types of states are called entangled. When we talk about graph states in the future, what we generally, or I guess how we generally represent entanglement would be just by lines, and our qubits will be the circles that are connected by those lines. So this state will just be represented by two qubits that are entangled with, and that entanglement looks like this line, basically. And that's a graphical way of representing them. We'll come back to that. Right. So for these states, as we've shown, parity cannot be measured locally. You can't just measure each spin separately and then make a claim about what the parity value should be. So this means that there's some information, in this case parity, which is encoded in non-local degrees of freedom. So this delocalization of the parity information has its uses in various quantum technologies. And that's kind of the motivation behind why entanglement is useful. So just to give you an example, so here I just show you this qubit state, this two qubit state. In fact, this is known as one of the Bell states. So technically there are 4 Bell states. I'm going to show you what they are. But this is one example of a Bell state. So we've shown that the parities along the z direction are always parallel. So the value of the parity is always +1. But you can also show that if you were to measure the parity along the x direction, you will also find the value to be +1. So there are 2 types of correlations in this state, even though the spins are completely random. If you measure each of the spin of the qubits, you will find it to be equal, likely to be up or down. So there are, however, other possibilities for correlations. So here are all 4 possibilities, and those are called all 4 Bell states. So if you look at each Bell state, the corresponding correlation that you will find in terms of the parities along the z direction and parities along the x direction are given here on the right side. So you can have all possible correlations if you want. You can have them to be parallel along the z direction, anti-parallel along the x direction, the other way around, etc. And all of this happens while the spins are, if you measure each of the spins or any of the spins, you will find them to be randomly oriented. So this type of a correlation, these correlations are not encoded in the individual spins of your qubits. That's why belt states are interesting. So I want to give you, so with that said, I want to give you an example about where entanglement is useful beyond just 2 qubits, because you might assume that 2-qubit entanglement is where it stops, but that's not true. So I can give you an example here with quantum error correction. So typically what you have with error correction is that you have a state of a qubit that you want to protect. So let's say it's this state. It's just some superposition that you care about. And the errors that you want to protect your state from are those bit flip errors. So bit flip errors are described by a Pauli X operator. So there's some probability that a Pauli X error will happen, where if you were in state 0, you will flip to 1, or if you were in state 1, you will flip to 0. Right? There's some small chance an error like this will happen. What you could do to counteract this is that you can prepare a 3-qubit state, right, where the coefficients are given exactly by the coefficients of the state that you care about. So the alpha and the beta here are the exact same coefficients that you will try to encode a 3-qubit state in, or prepare a 3-qubit state in, right? And you prepare them in this very exact way, where they're in a supervision of them all being in the state 0 and all being in state 1. If you think in the language of the correlations that we just talked about for Bell states, here you have 3 types of correlations, right? So you can talk about the parity of the first and the second spins, second and the third, and the first and the third. And in this case, they're all parallel to each other. So all those parity values will be +1. And you can use those correlations to determine whether an error has happened or not. So just to show you how that works, think of the middle qubit getting flipped. So this is an error, undesired error. We don't want this. So if you were to measure the parities now, so measure Z1, Z2, so that'll tell you whether the first and the second qubit are parallel or anti-parallel. So you'll find the value -1, meaning that something wrong has happened. If you measure the parity between Z2 and between the second and the third qubit, you'll also find -1. So that means that there is an error that has happened between qubits 2 and 3. So if you make an inference, so just from those 2 observations, so if Z1, Z2 are anti-parallel, meaning that one of the qubits of 1 or 2 has flipped, right? So the way to tell is that now we measure the parity between the second and the third qubits. So here we measured it and we saw it flipped also, meaning that either qubit 2 or qubit 3 was subject to error. And from here, we can conclude that qubit 2 must have been the one with an error, right? And just to confirm that, if you measure the parity of 1 and 3, qubit 1 and qubit 3, you'll find them to be +1, meaning that they are parallel, which is how they were originally. So nothing happened to qubits 1 and 3. So just by measuring the correlations, we can infer that qubit 2 was the one that got flipped. And you can also have similar types of correlation measurements if the first qubit were to flip or the third qubit were to flip. And this allows us, as soon as we determine which qubit was subject to the flip, we can flip that qubit back and we can correct our state. And that's the whole idea behind error correction. And as you can see, it relies on these types of correlations that are not local to any specific qubit, similar to the belt states that you saw. And one last example before we move forward. So I want to also mention quantum sensing. So here the idea is different from error correction. So what the goal is that, let's say you have some parameter that you care about. In this case, here in blue, you have some material, for instance. And once you pass a laser or some photons in it, it will accumulate a delay phase, right? A delay phase phi, let's say, that you care about measuring in some material, for instance. And the problem of quantum sensing is that you want to find out what are the best states you can send through this material to identify the true value of your parameter form. And the way it works is that you send some states, let's say n photons or n qubits, you send them through this material, and whatever comes out, you just measure, and just based on the measurement outcome, you make a guess. So it's well known that if your qubits were not entangled, then you would expect your guess to have some variance that scales as 1 over n. So the larger the number of qubits, the better your guess, because it has less of a variance or less of an uncertainty. But the scaling is 1 over n. However, if you have an entangled bunch of qubits, specifically these types of states, which are called G8Z states, then turns out that your estimate, or the variance of your estimate, scales as 1 over n squared. So it shrinks down, your uncertainty shrinks down much faster if you were to start with an entangled state like this, rather than just a bunch of qubits that are prepared separately. So that's another application of many particle quantum entangled states for a specific application, in this case, quantum sensing. So the claim is you don't only need to care about 2-qubit entanglement. Here you have many qubits that are entangled, and these states are still useful. Okay, good. So with this said, this kind of motivates our approach to graph states. So graph states are a type of entangled many qubit states. And these are the ones that we saw so far. So just to give you a general definition of what a graph state is. So think of a graph, so a bunch of vertices or and edges. If you want to think about a graph state, what you will have to do is think about each of the vertices as qubits being prepared in the plus state, and each of the edges in your graph as being a control Z type interaction between your 2 qubits. And a control Z is just given by this matrix in the computational basis, right? So that's all of what a graph state is. It's just a specific preparation of a qubit, of the individual qubits, and then making them interact together with this CZ gate type interaction. Now you might ask, this is part of a, this is kind of a random or not so, like, what is the motivation behind this specific definition? Because we could have defined it in various ways. Why this specific definition? So the reason, I suppose, is mainly historical. So this goes down to the 2001 paper, where the authors discussed how one can utilize a 2D and a 3D array of spins that are interacting in an Ising type interaction, meaning that there's a neighbor-neighbor interaction between those spins, and they're coupled with a ZZ type coupling. So this is very common for Ising chains. They're very good models for many physical systems, and the authors were interested to see what kind of an application these types of systems can have. So that's the kind of like the historical reason why graph states were defined in this very specific way. Right. So okay, let's as an example, let's see if Bell states could be related to graph states. So think about the Bell states that we saw before. So this is one of the Bell states that we worked with, right? The only difference here is Malin notational. So you saw spin ups and spin downs for your qubits. Here you're seeing zeros and ones, but it's exactly the same state. So I switch notations here just for convenience. Now, in terms of the correlations of the state, if you recall, if you were to measure the parity along the Z direction, you'll find it to be +1. Parity along the X direction, also you'll find it to be +1. Now, assume that you apply a Hadamard gate on the second qubit. So you start from this state, so you have the Bell state, and now you apply Hadamard on the second qubit part of that state. So the 0 becomes a plus, that's what you have here, and the 1 becomes a minus, right? So this is the state that you obtain. And indeed, you can write this state as a CZ gate between the first and the second qubits, where each of your qubits are prepared in the plus state, right? And this is very simple algebra. You can test it out yourself, and you can indeed verify that you can write this state in this form. But this form, as we saw, is a graph state, right? So we saw that this is a graph state where you have two qubits, each is prepared in the plus state, and there's just one CZ operation happening between them, right? So when we refer to Bell states, we typically say that they're locally equivalent to a graph state, meaning that if you just apply some operation, in this case a Hadamard gate, on one of the qubits, these operations have to be Clifford operations. So Clifford meaning that you have a Hadamard gate or a phase gate or a C0 gate. So if you, in this case, you're applying a Hadamard gate on your Bell state and you're obtaining a graph state, this just means definitionally that your Bell state is locally equivalent to a graph state. Right. Now, the difference with a graph state is that the correlations no longer have the same meaning in terms of the parity. So here, if you look at what the correlations of the state is, it's not the parities of the spins along the z direction and the parities along the x direction that we saw for Bell states. In fact, it's kind of a mixture between the z spin of the first qubit and the x spin of the second, or the x spin of the first and the z spin of the second. So it doesn't have that nice interpretation of parities that we had for spins that we talked about in the beginning of this presentation. Right. So this requires us a bit of a more formal way of thinking about correlations. So that's what I want to talk about in the next slide. So we can think about our graphs in terms of those correlations. And the usual language that people refer to this with is stabilizers. So when somebody says, let's say that an operator K is a stabilizer for a state psi, what they mean is that psi is just an eigenstate of that operator K with an eigenvalue plus one. So that's what a stabilizer means. So if K stabilizes psi, it means that K acting on psi just gives you back psi. Right? An example is that the operator Pauli X just stabilizes the plus state. Right? So if you act by X on plus, you'll just get the same state back. And we also saw that for Bell states, so for instance, the Bell state we just worked with, XX and ZZ are the stabilizers, meaning that if you act by them on the state, you will just get the same state back times plus one. Right. So stabilizers, this is a formal way of thinking about correlations. So that's what they're useful for. For graph states, these stabilizers have a very specific form. You've signed this form in the previous slide. But generally, if you have a graph made out of n qubits, then you have n stabilizers. All of them have this specific form where there's a Pauli X for instance, the stabilizer corresponding to the ith qubit. You have Pauli X on the ith qubit times Pauli Z for each neighbor to that qubit. Neighbor meaning that they're connected in that graph. So that's how a stabilizer looks like for a graph state. And finally, if you have two stabilizers for your state, then the product of those stabilizers is also a valid stabilizer. That's important to keep in mind for what comes next. So I want to give you an example and just work through it a little bit. So the claim is that this state that you see is just a graph state that corresponds to this graph. And the common eigenstates of, the common eigenstates with an eigenvalue of plus one, meaning the stabilizers of the state are just given like this. Right? So let's first of all, let's work through why this is a graph state. So let me switch to my iPad and start drawing. Okay. So let's see. Okay, so we're interested in this state, right? Now, let's start with with 3 qubits just separated from each other. So the graph that we're starting from is this. Just 3 qubits that are completely separated from each other. So the state corresponding to this is given by just 3 qubits, each of them prepared in a plus state. Right, so that's how we start with. That's the way we should start thinking about graph states. Is each dot represents a plus state. So here we have just 3 plus states. It's qubit 1, qubit 2, qubit 3. Right, and then what we should do is look at how the state changes when qubit 1 and qubit 2 interact via a CZ gate, right? Because we ultimately want to obtain the state on the top. So if the first two interact by a CZ gate, then you have a new state that's given by a CZ gate between 1 and 2 of the original state. Right? And this is simple to calculate. So just to show you, so CZ gate, we can expand this guy, right? So this is 0 plus 1. Acting on plus. And then there's a plus, right? And if qubit 1 is in state 0, nothing happens to the second qubit. So here this is just 0, 1, plus 2, right? Plus, if the first qubit in state 1, then the plus flips to a minus for the second qubit, right? That's how a CZ gate works. So this is 1 and then minus for the second qubit. And then you have a plus for the third. So nothing happened to the third qubit, right? So that's how the state will look like after one CZ operation. Let's rewrite it again. So it's going to look like this. Right? And now we want to do the final step, which is to do another CZ gate, this time between qubit 2 and qubit 3, right? So that will give us the final state, hopefully. So psi 2 is just CZ between 2 and 3 of the previous state, so psi 1, right? And we'll do a similar algebra. So what that means is, first of all, the state of the first qubit doesn't change. And then what you have is a CZ gate between 2 and 3, where the second qubit is in the superposition state. Right? Just using the previous state we found. So I'm just expanding that state with respect to the second qubit. Right, so we just wrote down what the plus and the minus are for the second qubit. And now we just act with the CZ gate. And that gives us the desired final state. So what we'll have? We'll have 0 plus, oops, this is the second qubit. Apologies. Okay, 0. And if the second qubit is in state 1, then the plus flips to a minus. Sorry, correction. This is the second qubit. So second qubit. Right. Good. Okay. Yeah, sorry for the confusion. But okay, so yeah, so CZ gate acts on the second qubit. So the second qubit is 1, then the third qubit flips from from a plus to a minus. So that's what we have here. Plus, we do a similar algebra on the other side. So in state 0, the plus remains a plus. And then if your state If the second qubit is 1, then the plus flips to a minus. And now all we have to do is to collect the terms. So here, this term and this term can be collected, right? And I'll give you this guy. Also, this term and this term could be collected. And I'll give you this guy. Right, so that's how we derive the state. It's a little bit of an algebra, but it's as you saw, it's pretty straightforward. So you start from the definition of a graph state. So just start with your qubits prepared in the plus state, and then one by one apply CZ gates to find what the final state will be. So in this case, we did it in 2 steps, right? We did the CZ gate between 1 and 2 first. We found the state, and when we did a CZ gate again between 2 and 3, and then we found the final state. And in terms of computing the stabilizers, so it's pretty straightforward to validate that if you apply x1 and z2 on this state, you're just going to get the same state back. I can just show you briefly. So just apply, let's see. Right, so just we apply x1, z2 on plus 0 plus, you'll just get the same, plus 0 plus. And if you apply it on the other part, minus 1 minus, well, you're going to get a minus from the x1 side, so minus 1 from here, but also you're going to get another minus 1 from there, and they're going to multiply. Then I'm going to give you a plus 1. So what that means is x1 z2 acting on your state plus 0 plus plus minus 1 minus just gives you the same state. Plus 0 plus plus minus 1 minus. And so on. You can do the same thing for the other 2 stabilizers. Right. But so that was mainly about the definition of graph states, or how we can think about them in terms of those correlations, or now we're calling them stabilizers, which is the technical term. Now let's talk briefly about how we can manipulate graph states, specifically via measurements. So here's a picture of how measurements change graphs, right? So we're talking about single qubit measurements. So if you're, the simplest thing to imagine is if you're measuring the Pauli Z of some spin. Let's say you're measuring the Pauli Z of this spin. So all that does is that it disentangles that specific spin or that specific qubit from the rest of the graph. So you're going to end up, if you start from this graph, you measure the spin, the Pauli Z here, then you'll end up with the same graph, except that now you removed all the connections that that qubit had to the rest of the graph. Right, so it's in the graphical term, it's very simple to understand how a measurement of Pauli X looks like. Pauli Y is a bit more complicated. So if you want to measure Pauli Y, what will be different first is that you will also disconnect all the connections that your qubit had to the rest of the graph. So here those connections will be gone, right, in the new graph. But what the difference is now is that you will look at the neighbors and you will study whether they were connected to each other or not. And then you will flip that status. So if they were not connected to each other, you will connect them. If they were connected to each other, you will disconnect them. So the example here is that the neighbors of this qubit are these 2, and these 2 are clearly not connected. So after you remove this connection, these 2 connections, you will also have to connect the neighbors because they were originally unconnected. So you'll end up with this additional connection that you didn't have in the Pauli Z measurement case. And conversely, if you were to measure the Pauli y of this qubit, and you look at the neighbors, those two neighbors. So if the neighbors were connected, then after you remove the connection of this qubit with the rest of the graph, so these two connections, these two blue lines, you will also have to change this connection from existent to non-existent. So you have to remove this. So there's this additional step beyond just making the Pauli Z measurement. Pauli Z will just remove the connection of that qubit with the rest of the graph. Pauli Y will do that, plus this additional step of changing the status of connectivity between its neighbors. And you have to do this for each neighbor pair you see. Pauli Z is slightly more complicated. But what will happen is that if you have two qubits that are neighboring each other, and you make a Pauli X measurement on both of them, then those will just take the qubits out of your graph, and the rest of the graph remains entangled in the same way they used to be. So this is how it will look like. But this works only because these two are neighboring. The rule can get more complicated if there's a specific, if you're looking into more complicated graphs. So just to show you an example of how this works. So think about this graph state. So you can do a similar analysis of why this is a graph state, but we won't do that. If you start by measuring the Pauli Z operator, so let's say you measure the Pauli Z on the fourth qubit, a subtlety that we have to remind ourselves is that that qubit will be removed from the graph state, but there's an operation that we have to do. So that one I didn't mention in the previous slide. Here I'm mentioning it, that based on the outcome, you may or may not have to do a certain change. So in this case, if you measure this fourth qubit and the outcome is 0, you don't have to do anything. You just will end up with just a 3 qubit graph state. If you measure that qubit and find the answer and find the Pauli Z to be equal to 1, then all you have to do is to apply a Pauli Z on the third qubit, and then you will end up with a graph state of 3 qubits. So there's that additional operation you have to do based on the measurement outcome. That's the slight subtlety from the previous slide. Same for the Pauli X. If you're measuring Pauli X, let's say on qubit 1, then qubit 2 will also separate, and you'll end up with qubit 3 and qubit 4 in a cluster state. So you'll have a 2-qubit graph state. You don't need to do anything else if you measure the plus for your Pauli X. But if you measure the Pauli X on the first qubit and find a minus, then you have to do an additional operation. And the additional operation is that you have to do a Pauli Z measurement on, you have to apply a Pauli Z gate on your third qubit to finally end up with a 2-qubit graph state. So those are the subtleties that you have to keep in mind, is that based on the measurement outcome, you may or may not have to do a single qubit operation. All right, so this is the first part of the talk. So in the next part of the talk, I'll talk more about the applications of these states, but hopefully at least this part gave you some idea of what graph states are, why we're interested in them, and how they change based on what we do to them. Okay, thank you. Thank you for listening.